Well, thank you, everyone. That's quite the introduction, for my first time being introduced like that. But it's great to be here with you all today. I'm Timothy Lee, head of platform at Theta Labs. So today I want to be talking about who we are as Theta, what the problem space is that we're getting into, how we're addressing it, fundamental questions like why blockchain is needed for the solution that we're coming up with, and then we'll get into some of the technical underpinnings for what we've developed as a blockchain protocol. And then I'll talk a little bit about some of the ways that we have taken to get market traction and user adoption. So just first, a little bit about who we are as Theta. Our co-founder, Mitch Liu, is the CEO. Jie Long is our CTO. Mitch is a serial entrepreneur, and Jie has also done his startup in the past as well. A little bit about our company. Theta launched as a project in August of 2017. We completed a $20 million private token sale to accredited and institutional investors, no ICO, in January of 2018. Theta and Sliver, as one company, we've raised $17 million in equity financing from some of these VCs that we have up here in the top right. So we have the traditional Silicon Valley VCs, the media strategic investors, corporate investors like our friends from Samsung and Sony. They've been really helpful in introducing us to different business units within their company, and then some of the blockchain companies as well. Our current partners, some of them have been redacted, unfortunately, but our go-to-market is very much to partner with a lot of these enterprise partners, doing a top-down approach, as well as growing a decentralized grassroots approach from the ground up through developers. So Theta is the leading video delivery network on the blockchain. So we're a decentralized peer-to-peer network. And so we're in the same space as a lot of the centralized content delivery networks, the CloudFronts, the Akamais of the world. And the problem space is that we have video that's today it's 1080p for the most part, but it's going to 4K to 8K video formats to Ultra HD, and the amounts of video that will be consumed in the upcoming years will drastically increase more and more, even as more users watch more video. So there's a problem with today's content delivery networks, which is that there's a last mile delivery problem, especially in developing countries where users on the very edge are having trouble loading contents, watching videos, there's buffering, there's latency issues, and that's just because these content delivery networks who are centralized have a physical infrastructure footprint, but it's not wide enough to address all the edge users, especially in developing countries. So we feel that our approach of decentralizing this, using a decentralized mesh network of peers on the edge to serve other peers and relay video and data to other peers at the edge will really help address this problem. The addressable market here, as you can see on the diagram on the left, is that by 2021-2022, over 80% of all IP traffic on the internet will be video related, right? So it's a huge market, it's a huge use case, and this is why our solution is pertinent. It's a $20 billion video delivery industry by that time, so the addressable market is definitely there. On the right-hand side, we have a few key features of who we are as Theta Labs. So we're an infrastructure play. I think a lot of times when we mention that we do video delivery and video streaming, people say, okay, well, you're competing with YouTube, you're competing with Netflix. That's not the case. We are the underlying infrastructure on the bottom of them, and we're inviting them to come and build on top of us. We're open source. I think that speaks for itself. Our code is committed to GitHub in various repos. We're a new blockchain and protocol, so we were an ERC20 token up until March of 2019 this year. We launched our own mainnet, our own Theta native protocol with our own tokens, and that's largely to integrate a lot of these technological blockchain features that are specifically designed for high transaction throughput on the blockchain, catering to video delivery and relaying small video segments from peer to peer. And platform partners, like I mentioned earlier, we're working with a lot of enterprise partners, inviting them to come build on top of our infrastructure. So very basic, high level, taking a page out of the sharing economy playbook, right? In the same way that Airbnb is, you're sharing your living space, Uber, you're sharing your transportation, your car. With Theta, you're sharing your excess bandwidth and computing resources. So this diagram on the left is pretty basic. Instead of HBO, I think a more pertinent example here would be, imagine a live sporting event, like a big soccer or football game. And there may be 2 million, 5 million viewers watching this exact same stream. There's no reason why 5 million viewers would have to ping the centralized content server when perhaps 100,000 people can grab that stream and then relay it out and propagate that video stream out to other viewers that are concurrently watching it at the same time. And when those viewers do that, they're contributing to the Theta network, and they're earning Theta token rewards as an incentive. So these are basically some mock-ups, some design mock-ups and concepts that I hope can help convey what these tokens can be used for. Just a disclaimer that we're talking to some of these companies, but these are just mock-ups, concept mock-ups to start with. So with these tokens, you can buy premium products and services, right? You can rent an episode of your favorite TV show, K-drama, movie. With Netflix, you can perhaps put it towards subsidizing or fully paying for next month's video subscription. On the bottom right, you can disable ads like the model from YouTube Red. And then on the top right, for user-generated content, in real-life content, where there's content creators and content streamers, we can use the blockchain to automatically allocate a certain portion of your token rewards to go towards supporting the content creator or the streamer that you monetarily want to support, right? Because they need this substantial support in a monetary way. And this can be done through these utility tokens, Theta utility tokens. So we launched our mainnet in March of 2019. The left-hand side is a screenshot of our block explorer. The right-hand side is Sliver TV. Sliver TV is also a company that we own. It's an esports viewing platform. I think the closest comparison for here in Korea would be that of Africa TV. Think of it as a Twitch or an Africa TV with tight engagement mechanisms. And what we've done is we've been able to build Sliver TV on top of the Theta protocol. So it's the first DApp of the Theta protocol, which really helps us iterate not only for the DApp, but also integration points for future content and service providers and video platforms that will come and build on top of us. I really think that this is a differentiating feature, right, between us and some other blockchain projects. We're not pie in the sky, high-level thinkers. We do have that, but at the same time, we have a test bed of sorts, right, in Sliver TV. That's actually it's a commercialized product, and we have 3 million monthly active visits. So there are actual users and viewers using this product. But then it allows us to source different insights, like how do our users actually understand, whether they're viewing or whether they're earning these tokens, how they're earning them, if they don't understand how they're earning them. So there's a very tight feedback loop between owning, one of our first DApps and then integrating a lot of these features to incrementally improve on our protocol as well. So just really quickly, some mainnet integration statistics from Sliver TV. We launched in March of 2019. On the chart on the right, you see that in December up to February of 2019, our daily active viewing time per user was in the range of 123 minutes, right? So 2 hours, not bad. But then there's a step function increase right around February of 2019. And that's when we announced that all of the testnet tokens that users were earning would be transferred over to the mainnet. So at that point, users realized that they actually had utility of these tokens that they could, in the future, use to purchase premium products and services on our website with these Theta T-Fuel tokens. So then the step function increases by 53 minutes, 40 to 50% increase. on the left-hand side, we break that segmentation out a little bit more. In the blue bar shows only theta channels. So when users are only watching theta channels, which is for the most part of our website on Sliver now, the average viewing time goes up to 266 minutes per day, right? So blended channels is a mix of non-theta and theta channels, 176, and then non-theta channels is now down to 106 because most of the prime content now is on theta channels. The content creators and the streamers, they all want to be able to have their users donate and stream and share their token earnings to the content creator. And as an industry benchmark, we have Twitch on the very right-hand side in purple. They're at 95 minutes per user. So I want to show this to you because I think it really demonstrates solid evidence, right? Metrics that show the value of having this token economic model implemented on top of our protocol. And this really does increase user retention, user engagement to the tune of 2.5 to 3x compared to our previous metrics and definitely compared to Twitch as well. So now that I've given kind of an overview, a high-level overview of what we are, the problem space we're addressing, this is a blockchain developer conference, so I want to double-click now into some of the technical features of our blockchain. So like I mentioned, we have the first layer, which is a mesh streaming layer, the data delivery layer, and then we have that built on top of the blockchain. And what that allows us to do is basically we're able to append one microtransaction with one micropayment. So a microtransaction would be if I relay a 4-second video segment to one of the peers out in the crowd right now, there's a micropayment that's appended to it, which is on the order of 0.00001 cents or dollars, right? So too small to be denominated by traditional fiat currencies. But over the course of earning a couple of days or weeks or months, then the amount of tokens that you accrue really becomes substantial. And then you have a number of these monetization models that I mentioned earlier. Those things become possible now. So that's the basic structure for Theta, these two layers. So speaking about the mesh streaming and the data delivery layer right now, I think it's important to preface this by saying that peer-to-peer delivery of media content is not new. I'll be the first to tell you that. 20 years ago, you had Napster, you had Kazaa. I'm sure there's various implementations of that in the Korean market also, and you have BitTorrent as well. But the thing with these legacy peer-to-peer models, I guess you can call them, is that they hit a number of friction points and hindrances that really prevented them from gaining wide user adoption, right? It was very niche, and sadly to say, it was adopted largely for pirating content, right? So we've taken a lot of these pain points and we have specifically addressed them through our approach. So the first thing that we've done is that we've looked at, the legacy peer-to-peer solutions. They have always required downloading a software client. And anytime you ask a user to download anything, that automatically rules out perhaps 80 to 90% of the user base, right? It's just too big of a friction point to overcome. So in our integration with a number of our enterprise partners, everything is seamless. Right when you hit the video stream, a blockchain wallet address on Theta is generated for you, even if the user is not logged in. So we're doing this by integrating with the app through an SDK of ours or through the video player itself with a few lines of JavaScript code on PC, desktop, web. So another thing was the incentivization models of these legacy peer-to-peer systems. You take BitTorrent, for example. A really popular mechanism was a tit-for-tat type of model, right? So you have an arrangement where if you wanted to go onto BitTorrent and say you wanted to download a movie, and it was 2 gigs of data, you had to upload 2 gigs of data in order to download the 2 gigs of data, right? So there was no outward reason for users to continue to contribute on the network after they've downloaded that movie. They shut their computer down or they take their node off of the BitTorrent network and they cease contributing. So it really relied on this altruistic tendency of the community to continue to power it, which had various levels of success. You could argue that it was very niche, like I mentioned earlier. So what we've done is we've essentially turned that model upside down, where instead of a negative reinforcement model where you're punished for doing something that, or you're punished for not doing something, we're making it so that you're rewarded for doing a favorable behavior. So our mesh network depends on a plethora of nodes all around the world contributing their mobile devices, their PCs, their smart TVs, their TV set-top boxes, perhaps their small server rig that they have at home onto the network. And you can imagine that a user, once they're done watching TV or and they're ready to go to bed, they can still keep their node, whether it's a computer, whether it's a mobile phone, on and contributing to the Theta network overnight, and they're earning these Theta token rewards as they're doing it. So that's, that small paradigm shift is what we think, and what's been demonstrated earlier is how we're going to really, transform this user adoption type of mentality and get mass market adoption. So talking a little bit about the architecture of the mesh streaming network, we have 3 global caching layers, you could call them. So at the very basic level, you have a viewer, a casual viewer that doesn't know much about crypto, doesn't know much about blockchain. So they're just watching the same video stream that they would always be watching, but at the same time, after they opt into contributing to Theta, they're able to serve that video stream that they're watching to 2, 3, 4 other peers that are concurrently watching that same stream. So that's the most casual viewer. And then we have the edge cacher layer, which is basically for power users or hardcore users that understand the technology a little bit more. They understand streaming. They understand that they would be serving as an edge server at the very edge of the network. And these ones, they dedicate perhaps some hardware to the network, and they will be able to simultaneously serve multiple streams at the same time, up to 50 to 100 people, viewers that are watching these streams. And then the last caching layer is the legacy CDN, which I just mentioned. Our go-to-market is not to ask these enterprises to really swap out their existing infrastructure yet, right? That would be very infeasible and impractical at this point. So it's always falling back to the CDN. And so if there's no viewer and there's no edge cacher that can serve a third-party node that is requiring a certain video stream, it's always falling back to the CDN. So there's no degradation or decrease in the quality of service to these viewers. There can only be a potential upside to these viewers through earning tokens, and potential upside to these video platforms and content service providers by offloading a certain amount of bandwidth. So we're supporting a number of device platforms right now. We're on PC, mobile, TVs. We're just moving into smart TVs and TV set-top boxes. We're finding that the compute requirements for these TVs and set-top boxes is not that high for just relaying and contributing excess bandwidth. And so we're targeting the video streaming use case right now with a future vision of getting into all types of static content, advertisements, static video files, game patches, and other things of that sort. So now let's talk about the blockchain layer. So we're really taking care of 2 things right now. And let me jump ahead to a few slides. So our key focuses, right? So I'll talk about the first 2 on the left here, and then we'll get into some slides diving into the technical details. So what we're really looking to do is increase transaction throughput for a video use case. Like I mentioned, every small video segment should be batched together in some sort of way, in some sort of layer 2 solution, and then that way the blockchain doesn't get overwhelmed by these numerous high volumes of small microtransactions. Scalable distributed consensus is something that we would really like to work on, and that's something I'll talk about next. And then these last 3 on the right are basically how we're working with our enterprise partners and how we're working with our viewers so that we enable this intuitive, seamless user experience that users they may not have to understand blockchain at all, but they'll be able to reap the benefits of the token economic rewards that we're providing. So we'll get into scalable distributed consensus first, and then I'll come around and I'll talk about the rest later. So with scalable distributed consensus, I'll set the basic context here, which is that you have a large set of nodes connected through unreliable networks, and the point of it is to get to consensus on a point of truth, get to agreement. And so within this paradigm, we have this impossible triangle with throughput, decentralization, and consistency. And it's widely believed that you can only have two, where you sacrifice a little bit more on the third component. So our consensus mechanism, we're starting off with a PBFT approach. So why PBFT? PBFT has been demonstrated to be able to support excess of 1,000 TPS, and also it's been demonstrated to be able to support safety and guarantee safety even in asynchronous network states. So we'll take this PBFT approach, and the first step is to allow permissionless access. It's very basic, but it's kind of a walkthrough for how we're thinking about our multi-level BFT. So we want to allow permissionless access to every node in the network. And a vanilla implementation of PBFT doesn't quite cut this, because we open the possibility of Sybil attacks, where you have one node that only has one vote. You open the possibility of a number of malicious nodes coming into the network and overwhelming these honest network nodes. So what do? There's been various implementations where you basically weight the voting power of a node based off of the amount of tokens it holds, or the amount of stake that other nodes will stake to that node. So that's essentially a DPoS type of implementation. So that's great. The step 2 is now to enable more nodes to verify the blocks. And numerous chains, almost all chains, allow users to run a full node, so they can download all the contents of the blockchain, and then they can start monitoring the state of the blockchain. The only difference is that these nodes cannot actively participate in proposing blocks, and they don't get the block rewards that are proposed from this block committee, or the block proposition committee, which is the validator committee. So in this diagram on the right, hypothetically, we have 4 validator nodes. They form the validator committee. They're proposing blocks. Our third step is our big step forward, right? This is our big innovation, which is to allow mass participation in the consensus process. And the way we do that on the diagram on the right is we still have the validator committee of these 4 validators, but we surround them with a second tier of consensus security that we're calling guardian nodes. So the guardian nodes will help to validate and vote for blocks. They'll also be rewarded for validating these blocks, and then they'll need to deposit a certain amount of stake. So what's the guardian node arrangement look like, you might ask? We're targeting in excess of 1,000 guardian nodes. And so the logical next question that follows that is, great, it's good to have 1,000 guardian nodes to serve as a second layer of consensus that would check and verify the blocks that the validator committee proposes, but how is that actually possible, right? You have communication overhead. If you have 1,000 nodes, you might have 1 million messages being transferred throughout the network at any given time for these 1,000 guardian nodes to come to consensus. So one way that we're proposing this is to implement these checkpoint blocks. And so what I mean by checkpoint block is being able to take a certain chunk of the blockchain, and so these guardian nodes will not vote on every single block, because that's the role of the validator committee. Rather, they're voting on each checkpoint block, and a chunk of these checkpoint blocks can be 100 blocks, or 50 blocks, or 200 blocks. And the reason we can do this, basically spot checking at specific intervals, regular intervals along the chain, is due to the blockchain immutability property, which is that in a header of each block, you have the hash of the previous block. So basically, if the guardian nodes agree on one block of the checkpoint block, they basically agree on the entire blockchain up until that block, or at least the entire blockchain up until the previous checkpoint block. So essentially what we're doing is we're chunking the blockchain, and we're having the guardian nodes vote on consensus for that. What this really allows us to do is it gives sufficient amount of time for the guardian nodes to reach agreement. So you basically have a comparison here. And so this strategy basically is kind of the inception of why we're calling it a multi-level BFT solution, right? So the first level is the validator committee. Our nomenclature here is that the validator committee proposes blocks, and these blocks are called settled blocks. And then after the guardian nodes vote on the blocks. At the checkpoint blocks, all of the blocks up until that one checkpoint block become finalized blocks. And once blocks are finalized in our chain, they become irreversible and irreversible state. So a side-by-side comparison, the validator committee, they work on block settlement. The Guardian network works on block finalization. There's a relatively small number of validator nodes compared to the Guardian network, although I should say that the Guardian network is actually a superset, right? So all the validators are actually Guardian nodes as well. Validators produce new blocks at a faster speed, and basically the Guardian network only finalizes the blocks at these various checkpoints. So having said that, we've implemented this checkpoint block type of approach. Have we gotten there yet, right? Can we achieve this this number of 1,000 Guardian nodes? With the naive implementation of an all-to-all broadcasting, messaging broadcasting, it's still very high. It's still very high complexity, right? And so it yields a quadratic communication overhead where simply it's too much for the entire network to come to consensus on, especially with 1,000 Guardian nodes. So what we're doing is basically we need to come up with a way to condense the type of messaging and the digital signatures that are being passed throughout the network so that we can allow for a larger number of participants to participate in the Guardian node consensus. So we're leveraging signature aggregation. So what this is it's basically a constant length signature that encodes the approval of multiple other Guardian nodes. And so that is, this diagram on the right shows that every Guardian node sends its own unique digital signature to the central Guardian node, and then the Guardian node collects it and then propagates it back out with a digital signature of the same length, but also with a compact bitmap of all the signers that are encoded in that bitmap as well. So one Guardian node basically collects all the digital signatures and then propagates it back out. So this communication complexity now is drastically reduced. We'll kind of walk through this animation. So now, with this simple illustration, it's still not enough because the central node might be a malicious node that would affect all the other signatures that have been propagated and compiled. So how do we guard against these malicious Guardian nodes? This is where we have the aggregated signature gossip. It's not just one Guardian node that does this. It's every Guardian node in our network that's contributing to this gossiping out of the aggregated signatures. And they're gossiped out until 2/3 majority consensus is reached. So this is basically a short type of animation where we'll walk through it really quickly. Oh, okay. So then Byzantine node handling is basically assuming that there are some Byzantine nodes in the network. This gossip type of propagation can route around these Byzantine nodes. I have 12 minutes left, so our resource-oriented micropayment pool is basically a layer 2 solution, taking inspiration from state channels and payment channels and basically customizing that for 2 nodes that are opening up a peer-to-peer relationship. And so they basically send these payment receipts back and forth to each other until the relationship is consummated and is closed, and then one payment receipt is sent to the blockchain for a token reward. So I want to talk a little bit more about the last 3 components, the seamless integration with existing infrastructure and this intuitive UX and design. Firstly, on this token usage, on Sliver TV, we're basically allowing our users to have a hybrid payment method, right? So you take a pair of these earphones, for example, headphones, and say it costs $300. If you have enough tokens, you can pay it all in tokens, or you can subsidize it a little bit if you just have a few tokens and you want to get maybe $20 off of it or something like that. So we're coming up with these concepts and these experiences to for users to intuitively understand it, and these concepts aren't foreign to them. It's just that we have to kind of weave it into an experience that they understand. And then finally, our DApp partners, the way that we're going to market, as I mentioned earlier, is not to approach these enterprises and say, we're a decentralized blockchain, which we are, but our approach is not to go up to them and say, you should swap out your existing infrastructure and then plop Theta in. Our starting point, at least, we're taking a very measured approach, is to be the supplementary layer that sits on top of their existing infrastructure. So that way we can offload as much bandwidth as possible, and then this allows the users to benefit from it, and then this allows the platforms to retain and engage their users a lot more as well. I think that's about it. I just want to say thank you for coming here and listening to this talk, and also thank you to our team back at home, our CTO Jie and our principal architect Rubao. They're really the minds behind this, and I get the privilege of coming here and presenting our great work from our great team to you guys. So thank you. I think we have some time for questions.
Before we let you go, we'd like to introduce some questions asked from the audience to you.
Sure.
And questions will be displayed on the screen, and if the question is not written in English, let me translate it for you.
Okay.
네, 티모시 총괄님께 들어온 질문 몇 가지를 함께 살펴보도록 하겠습니다. 첫 번째 질문입니다. The first question is, 사용자 PC에 놀고 있는 메모리와 밴드위스를 사용하는 것이 주된 특징인데 고화질의 동영상 스트리밍으로 인해 캐싱 로드를 운영하는 사용자가 컴퓨터를 사용할 때 자신의 PC가 느려지는 문제가 발생하지 않을까요? So it uses user PC's idle memory and bandwidth. When a user who operates caching node for high definition video streaming, the user may experience that their PC slows down. Isn't it a problem?
Yeah, so that's a great question. We're targeting, so there's various implementations, like I mentioned, in the global caching layer. So we're finding that if you're a casual user, right, you need to be able to, we're totally transparent about consent, so we're asking users to opt in, right? So if you're watching one video stream, you have the bandwidth and the capacity based on your internet connection to upload that bandwidth to 4 to 5 other 4 or 5 other viewers at the same time, and that typically doesn't require too much RAM on your computer to actually carry out. In the case of an edge cacher where you're serving numerous streams, multiple streams to 50 to 100 people, we don't recommend that to be run on just any desktop PC. I think that would require some more dedicated hardware. So we're really conscious, I didn't get too much time to talk about this, but we're conscious about bifurcating between the casual user who's just wanting to watch a video stream and perhaps get a discount or some token rewards to apply to next month's subscription, and the power user who understands this a little bit more, who has the technical savvy to dedicate a rig and software to supporting our Theta network.
Okay, thank you. 이제 두 번째 질문을 한번 같이 보도록 하겠습니다. The second question is, 에어비앤비와 우버의 예를 드셨는데 해당 서비스들은 결국 남는 자원을 대여하는 것이 아니라 대여만을 목적으로 전문적으로 참여하는 사람들이 대부분인 것을 감안하면 세타 네트워크도 결국 전문적으로 캐싱 노드를 운영하려는 사람들만 남지는 않을까요? 그렇게 된다면 기존의 CDN 서비스 업체들과 다른 점은 무엇인가요? You mentioned Airbnb and Uber as examples. Considering that such services participants has a pure purpose of renting spaces and making money, not a lending idle resource, SATA network will eventually have those who want to operate caching node professionally. If that's the case, what makes it different from existing CDN service providers?
Yeah, that's a great question. The difference is that these existing CDN service providers, they're operating physical infrastructure, right? Points of presence, which are basically their edge servers, but it's all centralized. So our vision eventually is to have these users within the Theta network operating as very edge types of caching layers or caching nodes, and so basically you're closer to the end user and the end viewers that need to pull these streams, and just by virtue of the definition of you being an edge relay node, right? So I'll give you a good example, I think, which is especially in Asia, in like very densely populated urban areas, you may have fiber, internet fiber that's running through the entire building, right? A CDN is always sitting outside of the building, regardless of how many edge servers they have, right? But imagine if you had a number of edge cachers that are actually operating within your building. Those edge cachers would be able to serve everyone else that's watching a World Cup game or something like that over IP. So that's really the difference. We're getting to the very edge compared to a CDN, which has limited capability because at the end of the day, they're still centralized.
Okay, thank you. 네, 마지막 질문, 시간 관계상 마지막 질문을 보도록 하겠습니다. This would be the last question. 결국은 전문 기업이 하던 CDN 서비스를 일반 사용자가 제공할 수 있도록 하고 그에 대한 보상을 제공하겠다는 것으로 보입니다. 하지만 전문 CDN 서비스와 달리 일반 사용자는 사양도 낮고 많은 양의 동영상을 저장하고 있지는 않을 것입니다. 그러면 결국 전문 CDN 서비스를 사용하는 것에 비해서 캐시 힛 비율이 낮아 오리진 컨텐츠 서버의 트래픽을 낮추는 효과는 적어지지 않을까요? 또한 시청자 입장에서는 좀 이 동영상이 느려질 수도 있을 것 같습니다. So you are basically enabling general users to provide CDN service, which used to be done by only professional companies, and give the users compensation. But unlike the professional CDN service providers, average users may not have enough spec and enough video. That means cache hit will be lower than using professional CDN providers and make the effect lowering the origin content service traffic insignificant. Also, from video viewers' perspective, it may be slow. What do you think on that?
There's a couple of points in here. I'm not sure I understand the whole question, but I can address at least some of it. I think the point of it is to decrease the amount of traffic coming from or hitting the origin server. One of the great benefits of offloading a lot of the bandwidth from these video platforms is that it directly translates to cost reduction for their content delivery network costs, right? So say that a Netflix or an HBO, I'm not sure of any Korean video platform, is paying all of their money to a content delivery network. If we're able to offload 40, 50, 60% of those content delivery network costs to the Theta Mesh network, then that effectively goes to lower 40 to 50% of their content delivery network costs to those CDNs. Definitely, I understand the spirit of the question, I think, which is that there may be inadequacies with some types of hardware specs. We're very cognizant of that, and we're able to, basically allow the user to opt in to when they want to contribute their hardware or their bandwidth to the network and when they won't want to. So a good example is if you're on LTE with a mobile data plan and it's not unlimited, you can maybe switch off your Theta network contribution when you're only on LTE data, and then when you switch over to Wi-Fi or some other internet connection, you can continue to operate on the Theta network. Hopefully I've addressed this question, but if not, I'm happy to take any questions offline as well.
Thank you.
Yeah.
So in the interest of time, I'm afraid we should wrap it up here.
Okay, thank you.
Once again, thank you, Mr. Lee, for the presentation and the kind answers. 아쉽지만 시간 관계상 여기서 마무리를 하도록 하겠습니다. 좋은 말씀해주신 티모시 리 총괄님께 다시 한번 큰 박수 부탁드립니다.